And welcome to our final help video on the 6C10 valence shell electron pair repulsion or VSEPR shape quiz. Our final video picks up with part 4 dealing with the selenium hexafluoride or SEF6 molecule. Let's go ahead and draw this, starting with how many electrons should be on this molecule. Selenium is in Roman 6. So it has 6 valence electrons. The fluorines are in Roman 7. They have 7 valence electrons. 6 times 7 is 42. We're working with 48 electrons. Selenium needs more bonds. So it will be the atom in the middle. It needs 2 bonds, but here it's going to make more than 2. As we'll see, it has to make at least 6 to get the fluorines on there. But selenium can do that. Selenium can make more than 2 bonds. It can be expanded, because selenium is from the 3rd level or period on the periodic table downward, which means it has a D that can be used for bonding purposes. When selenium ends up with more than 8, it still has the 8 it needs. It's said to just be expanded beyond the 8. So let's go ahead and put selenium in the middle, and we will surround it with 8. So we have selenium in the middle now, and we've surrounded it with 8, and we have to attach the 6 fluorines. So I could put a fluorine here, fluorine here, fluorine here, and a fluorine here on this pair, on each of those sides. But I still have 2 more fluorines to attach. So, I can go ahead. I know they're on the molecule, so I can go ahead, if I want to do it this way, and just put the extra pair there that I'm going to attach. That'll get that one on, that'll get that one on. I slide this pair over here. I know I need to get them on, and I need to have an electron pair for them to go on, so I go ahead and put those fluorines there. Or those electron pairs there. That pair's for this one, this one, this one, this one. I can get all the fluorines on now. And then I'll surround the fluorines so that they all have 8 total, putting 6 more on each of the fluorines to give them 8. Sometimes it cleans it up a little bit if you just do the lines on these expanded octets right away, so it doesn't look like we've got this encirclement of selenium with electron pairs. So I'm going to go ahead and replace these pairs with lines and surround the fluorines with 8 total. So as we've mentioned, we had 48 electrons to work with. We have 48 on here. We have the 6 fluorines, each with 8 around them. 6 times 8 is 48. So it looks like our molecule has been completed, and we will be able to analyze this molecule now using the valence shell electron pair repulsion theory. Again, selenium has been expanded. It can be expanded because it does have a D. It's from the 3rd level down. In fact, a selenium has 2, 4, 6, 8. What is that? 12 electrons in its valence. How many total atoms are around selenium? There are 6. We count atoms, not bonds. How many lone pairs are there? There are none. So we have 6 total things surrounding the central atom. That gets us to 21's answer. When you have 6 things around it, it is octahedral. Which octahedral is it? Well, there are 3 possible octahedrals. Here's the octahedral family. We have the octahedral shape as a member of the octahedral family. The family is named after the first one in each of those, the one with no lone pairs. There's also square pyramidal, which is 5 atoms, 1 lone pair. Square planar has 4 atoms, 2 lone pairs. This one we're looking at, we had 6 atoms, as we saw, and 0 lone pairs, as we saw right up here. 6 atoms and no lone pairs on the selenium central atom. So the 6-0 is octahedral, so we can circle letter BD. With the 6-0, our shape formula, our B was 6, that's 6 bonded atoms. Our lone pair was 0, it's a 6-0. The 6-0 is the octahedral shape. Here is what it looks like. It is letter BD. We'll circle that. We were not asked for the bond angles, but if we were asked for the bond angles, the axial atoms run through the axis. The equatorial atoms, there's 4 of them, are on the equatorial plane or the equator, which goes around this direction. So what are the angles between the 2 axials? One up, one down. That angle is 180. What are the angles between the equatorial? Well, there are 4 atoms making up that equatorial plane. The plane, if we go all the way around one time, it's 360. 360 divided by 4 is 90. Each of these angles between the equatorial atoms are 90. What's the angle between the equatorial and the axial? Those are also 90 if we were asked for those angles, but we weren't. The next thing we're asked for, number 23, what's the symmetry? Well, this should be pretty easy symmetry, we hope. It's a 6-0, so the E is 0. There are no lone pairs. When there are no lone pairs, we pop out of the lone pair column. No lone pairs, E equals 0. We come down here, and it is symmetrical, provided that we have the same type of atoms surrounding our central atom. We go up and double check. Yep, they're all fluorines. They're all the same type of atoms, so this one is symmetrically shaped. All the same type of atoms and no lone pairs. It's symmetrical. There's only one polarity the molecule can have when it's symmetrical. We follow this path up or over, up, and right to the nonpolar molecule shape. So question number 25. What's the strongest intermolecular force on this one? It is a nonpolar molecule, which means it can only have London dispersion forces. Nonpolar means that there is no net dipole. There are no partial positives or partial negatives on this molecule. A London dispersion force isn't a full dipole or isn't a dipole where there's actual partial positives and partial negatives. London dispersion forces have something to do with the fact that the electrons are in constant motion on these atoms. So if the electrons move maybe from this atom and they move more over towards this atom, if they did, well, what would happen is that would leave this fluorine momentarily partial positive while the electrons went to the selenium. But fluorine will pull them right back. Likewise, the electrons with fluorine for certain can get pulled over to the fluorine a part of the time, making the fluorine partial negative for just the moment that they're there, until selenium can pull the electrons back. So the fact that the electrons are in constant motion, or the fact that an atom has electrons that are in constant motion. For instance, we have a fluorine atom right here. The electrons on this fluorine might move from one side of the atom to the other. That would leave one side of the fluorine atom partial positive. The other side of the fluorine atom where they move to would be partial negative. When you have lots of electrons in motion around the atom, it can give little momentary partial positive spots on the atom. We'll get more into London dispersion forces. I was trying to explain a 25-minute discussion in 30 seconds. In fact, from here, that is where we're moving to. What are the other type of intermolecular forces? Let's get a much better explanation as we move on forward. Thanks for watching the help videos on 6C10. If you have any further questions, don't hesitate to ask.